FIFTY2 Technology is actually developing the software called Prion Lab, very successfully applied in the field of automotive specifically, and one of the, I think, most prominent SPH servers out there. For all of you who are already a bit deeper into the science of SPH, there are different versions of SPH out there. And for example, weakly compressible SPH, incompressible SPH, and with FIFTY2 Technology, they are using the incompressible implicit SPH. Very interesting approach for everybody to check that out. And I think it's going to be a pleasure to see them show some interesting insights about how they are using the software in the field of water weighting successfully. Again, it's a pleasure to have him here. I'm very much looking forward for the seminar. With the questions, please wait until the end. I already wrote it into the chat. Either put your questions there or raise your hand and ask at the end. I'm looking forward to that session. And with these words, Marcus, I would hand it up to you. Enjoy it, and for everybody else, enjoy the session. First one out.
Good morning, everyone. As you might be aware, I'm the SPHERIC chair, and I would like to thank you for joining us in this very nice initiative. And also would like to thank you, Ben, Nathan, and Pierre for making the effort of organizing this new round of virtual seminars dedicated to SPH, and also obviously thank you to Marcus for accepting to give the first talk. As you might be aware, SPHERIC is the international organization representing the community of researchers and industrial users of SPH. SPHERIC organizes several initiatives around the world to promote research and use of SPH as the SPH numerical scheme. And probably the most relevant and established initiative are the SPHERIC workshops. And let me just remind you very quickly that in 2022, there are 2 SPHERIC workshops that are taking places. One in China, organized by Xi'an University, and it will take place between the 28th of March and the 1st of April. And the second one will take place in Catania, Italy, between the 7th and the 9th of June 2022. So if you are working on SPH either as a researcher or as a practitioner, you might consider to do 2 things. First one is to register on the SPHERIC website to become a SPHERIC member. It is free of charge. The instructions are reported on the SPHERIC website, and being part of the SPHERIC community, if you are active on SPH, has a lot of benefits. And the second thing you might want to consider is to participate either to participate to the SPHERIC workshop, and you might also want to submit an abstract and so share your activities on SPH with the rest of the community. So thank you very much again to all of you for joining us, and particularly to Marcus for giving this talk, which I really look forward to listen. Thank you.
Okay, thank you also very much, Renato. Thank you, Pierre, for the very kind introduction. So I'm really grateful and honored for being invited to present how and why our SPH-based solution is productively used in the industry. As this is here one of the grand challenges of the SPHERIC community, I hope you will enjoy the next 40 minutes. Before we start, let's look at the structure of my talk. So first, I would like to introduce our company FIFTY2 and myself. Then I will describe the purposes and challenges of the application at hand, which is called water weighting. And next, I will motivate why SPH can be considered the go-to technology for this application. Of course, not every SPH implementation is suitable for this task. There are certain key innovations necessary, which I will briefly explain. And at the end, I will demonstrate the advantages and applicability on a real-world use case. At the end, there should be a good piece of time left for a Q&A session. So Pierre already summarized it a bit. Maybe here some stations of mine. I'm a computer scientist, actually. I did my diploma thesis in 2006 on lattice Boltzmann, and then pivoted in 2007 to SPH with the focus of my PhD research to find algorithms, data structures, numerical changes to make the SPH particle-based method as efficient and as reliable as possible. Here on the right-hand side, you see a simulation that our group did in 2007. So this is what actually I started with. We were able to simulate 200,000 particles with a weakly compressible approach. And this simulation took 5 days to compute on an 8-core computer. So now, 14 years later, we are able to simulate hundreds of millions in the same time frame with higher accuracy. And to be able to get there, we put research effort in different fields. First of all, parallelization techniques and neighborhood search, where we published quite some papers. And what affects efficiency and robustness and reliability is interface handling, fluid-solid interaction. And there we published quite a lot of papers also for two-way coupling. So we have also a particle-based rigid body solver. And one of the key innovations is, as Pierre also mentioned, this implicit formulation, which we have invented or developed, which allows you to efficiently solve for the Navier-Stokes equation, for pressure and for viscosity with a low memory and computational footprint. So with all this research, we also have risen the interest of different industries and companies in this industry. And one of these were a company from the automotive industry. And they finally motivated us to found the company in 2015, where the first focus application was rainwater management, as can be seen here in this video. So in 2016, our first version of Prion Lab was launched. Now I should explain a bit what Prion Lab is. Prion Lab is our software tool, which we call an all-in-one tool, because you don't need a third-party tool in order to do simulations like we see here. As long as you have the geometries, then you can actually drag and drop these geometries into the software. You can script all the motions of the geometries, like the gears here and the bearings. And then you can simulate, of course, and then you have the option to place virtual sensors for measuring torque losses, wetting time, and whatnot. And you even have the possibility to do those photorealistic renderings. So we have a physically based ray tracer included in Prion Lab, which allows you with just one click to create such images and videos. But of course, Prion Lab is a tool for engineers, and it's more about just nice images. So it's very important that the results that are simulated are also reliable and predictive. And therefore, Prion Lab has proven that it's capable of doing so. We have a lot of different showcases and tests, which we make sure that this is the case for high volumes of water or oil, and also for smaller volumes, and including macroscopic and microscopic behavior. And we can even simulate different types of snow on a predictive level. It's even more, we are able to simulate highly viscous and non-Newtonian fluids with this implicit viscosity formulation. We have, as mentioned, this rigid body solver, where you can simulate, for example, the gearbox completely and just script the motion of the pinion. We are able to simulate multi-phase at low and high density contrast now, and also heat transfer inside the fluid and the solid and the exchange between both phases. So with this feature set, we provide, or the Prion Lab is used in several industries productively, for example, for optimizing the dishwashers. And as Pierre mentioned, also in the automotive industry, mainly our customers coming from the automotive industry there with the flagship applications in transmission and driveline, so for gearbox lubrication, churning loss prediction, e-motor cooling, and also for the full vehicle for soiling of different materials, snow or water, rainwater management, and of course, water weighting is one of the flagship applications. This is the focus of my talk today. So what is water weighting? Water weighting is a standard test in the automotive industry where a car drives through a channel which can be up to 100 meters long, and it has a slope in the beginning and at the end. And the car drives through this channel, which is filled with water of certain height. So this can be several millimeters up to half a meter or even more. And the car drives through this with different velocities, as we will see later. And the purpose of this test is quality assurance. So key points of interest are, for example, the water ingress in the air intake system, the wetting time of different components, and of course also the hydraulic forces exerted from the water onto the geometries of the car. And there are certain challenges for the development of a car, because this is a real-world standard test and this has to be performed at the end. But you need a full physical prototype in order to do it. You need a full car and you need a testing facility at hand. And if you have both, which comes very late in the development stage, actually at the end, the complex or the sensor setup is very complex, yeah, for placing the sensors. And once you have placed them correctly and the cameras and whatnot, you can only measure if your values are below or above a threshold. And if they are above and the test fails, then you have a problem, but you do not understand where this problem is coming from. So it's very limited. The engineers differentiate between two regimes: the subcritical regime, where we have a low velocity and or bigger or higher water depth. This looks something like this. And then we have the supercritical regime, where we have a higher velocity of the car and or lower water depths. And you see that here's already more action in the water, and there will be also higher forces exerting on the geometries. So you might now wonder why this is actually a problem at all for engineers, because you might think, okay, cars are built since quite a long time, and actually this should be common knowledge how to get this right. But actually the problem is quite significant for two main reasons. First, as exemplified here, the number of vehicles types built per OEM is increasing. So here you see the vehicle fleet of Audi in year 2000. And this is how it looked 15 years later. So you might imagine that small changes in the design and the technical equipment might cause significant changes in the weighting channel later on, which could not be anticipated beforehand. And this is bad, and this is even worse because the climate change related regulations have accelerated the development of new driveline concepts and increased the number of car manufacturers drastically. So the resulting design changes and placements of the functional components in the car are causing new questions and challenges for the water weighting quality assurance test. For example, the battery packs of an electric car are usually placed in the underbody region where hydraulic forces can be very high. And finally, increasing the number of sensors and cameras that are installed in a car, particularly for autonomous driving assistance systems. So here the number of sensors is increasing, and a good design maximizes the visibility and functionality of the sensors under all driving conditions. So we need to figure out how and where to place these sensors and cameras such that the functionality of the autonomic driving system is guaranteed. So according to this general environment, waiting for the physical prototype to be ready and do the testing after the development is quite risky and very expensive. And also it's very unflexible. Yeah. So this demands for a better solution, which can be offered with simulation tools. The automotive industry has a long tradition of using simulation to decrease development costs and time. But for waiting, traditional methods are not well suited. And I would like to explain now why. So look here at the exemplified workflow for waiting simulation using a traditional grid-based method. So first of all, we need the full car CAD data to be translated to a mesh, which actually can be used for computing the simulation. And as we need all the geometries of the car, this can be a very tedious and requiring manual labor work and can consume weeks of meshing. Then this data is transferred to a simulation cluster, and the simulation time is usually some weeks. And then you need to imagine that we are talking here about transient data that need to be transferred back then for analyzing it, and transient data for a real world period of 30 seconds or up to a minute. So a lot of data that will be consumed and need to be analyzed. And then just to exemplify, this could be one result here. You see a cut plane somewhere through the car, and now let's pretend that the yellow and green and red regions are bad. So this needs to be optimized. So then engineer will try to come up with some solution for the geometries. Some changes will be made. A new CAD model is generated, which needs to be meshed again, transferred to the cluster for simulation. And then some months later, we get this result, if we are lucky. So this is a very iterative process and very time consuming as well. But still, it's months and not years. But we can do better with particle-based simulation techniques. And that's why I'm here today. So with Prion Lab, for example, you can do these kind of simulations, setting up the simulation, doing the simulation, and getting the results in a time frame of days. So if you have used Prion Lab not for the first time, you can do the setup in half a workday. You run the simulation, which can take a day or 2 days or 3 days, depending on the resolution you're using and require. And then you spend some hours on the analysis and you have your insights. So this is what we promise here, shrinking the time frame from years to days. So this is more from a management perspective, now looking at the technical challenges for this application. Of course, it's not that easy. It's quite rather challenging because we have a large simulation domain. And here you see a cut view through the car, and you see that it has all the geometries in it. So very complex geometries. The car is moving through the channel. I mentioned in the beginning, it has a slope in the beginning, at the end. And there are small channels in these geometries which needs to be resolved in order to get the flow rates right. We are lucky here that this is a liquid dominated flow. This means that we simulate a single phase, neglecting the air phase is sufficient. So this is very good for SPH, for example. And as mentioned earlier, we need a powerful post-processing method, which is capable on processing a large amount of data, which results here from the transient data recorded throughout the simulation. And this post-processing might look something like this, that, we look at the area behind the air intake system, and there we measure that there's water inside, and now we do a path line analysis to understand where this water is coming from, and with these insights we can make changes, or engineers can make changes to the geometry to protect this part. So this is something where where simulation is very powerful, because this is not doable in real-world testing. So I mentioned that the challenges, so large simulation domain, but fine resolution needed. And yeah, so how are we doing it? How can we come to this performance that I mentioned? So first of all, I would like to highlight our implicit formulation, because it can capture the same or cover the same time period in real world time with much less computation time. So less time steps are needed. We can use CFL criterion up to 1, and therefore much larger time steps, as has been published in several publications. So overall speed up that you can see realistically is an order of magnitude or even higher compared to, for example, weakly compressible SPH. Of course, these computations can be optimized by using more computational power. We are using a hybrid parallel implementation technique. So this means that we use OpenMP to get the best out of shared memory systems, and we use MPI for the communication between computer nodes. And here you see that our approach scales very well compared to the theoretical optimum. So this is with respect to performance. Performance is definitely a crucial requirement to get feasible runtimes. But there's another key feature required for water weighting, which is car suspension. We will look at this simulation once more, and look please at the upper body of the car and how it changes its position in relation to the wheels, for example. And why this is so important, I would like to highlight on this slide here. If car suspension is disabled, the upper body of the car will be lower, and this changes the front wave quite significantly. Yeah, you might see also, I saw recently some videos of a traditional CFD method for water weighting. They try to advertise this now as well, where the full front part of the car was covered by water. So this won't work in reality. And so if you don't have a car suspension enabled, then you will have a higher water level, and you will predict more water inside the engine compartment area. And you will probably predict that there's more water inside the air intake system than would be in real world. And this is changing completely your insights that you gain from the simulation, which are wrong then. So again, if car suspension is enabled, the upper body is lifted. And this is computed in Prion Lab due to the hydraulic pressure forces. So the forces resulting from the water onto the body. And this then results also in a lower bow wave. Yeah, here you see the deflection curves for front and rear spring damper system as the car drives through the channel. And note please that this deflection, I just repeated, is computed out of the hydraulic forces of the water acting on the car geometries. The reason why I repeat this is also because now we will look at a real-world use case from Volvo, and there also pressure forces are compared, and also then with another, in comparison to another simulation tool. So this case study performed by Volvo was published in 2019. You can read more on this if you find this linked on our website. And the goal of this case study was to investigate the use of an SPH solver to work as a complement or substitute to their current method. So at this point in time, for weighting applications. So there were two objectives. First of all, compare the results predicted by the volume of fluid method, which was StarCCM plus, to SPH, which was Prion Lab version 3.3. So the whole test was performed, or the study was performed in 2018, 3 years ago. And the second objective then was compare SPH to physical testing. So there were 3 key measurement points, which were the water height, the forces, drag and lift forces on the exterior body panels as marked here in different colors. And the third point of interest was the water inside the air intake system, which is measured then through the sensor plane as illustrated here on the right. So in order to be able to compute, to compare the simulation results of the traditional method, so the volume of fluid method, with our SPH solver, a change in the reference frame was needed. So when they did water weighting simulation with star CCM, the car was put stationary and the water was moving. So just changing the reference frame. And therefore, some conditions need to be added because this is not usually used in our SPH simulations. We actually try to replicate what happens in the real world, also the movement of the car, because this comes for free. So we had to add some wall boundary conditions in order to get this setup right. Yeah, but this is possible, absolutely possible. And then you can compare those two simulation methods with each other. And here you see the results. So on the most right result image is from the star CCM simulation. The three on the left are all with Prion Lab for different spacings. All of these simulations are done with uniform spacing, so 10 millimeter down to 5 millimeter, and you see that the 5 millimeter results from general surface height, which is here color coded, is quite comparable to the one predicted by the volume of fluid method. Let us look at the pressure forces now, which are very interesting. So the volume of fluid curves, pressure force curves, are color coded in blue, and the ones for Prion Lab for the different spacings are in these other colors, as you see here. So basically what can be observed is that the Prion Lab forces are higher, but they are mostly in quite good agreement with the ones of the volume of fluid method. Except for the undershield and the side carrier, we see a deviation. And this can have different origins, as discussed also in the master thesis. For example, there might be small difference in the setup, the boundary conditions and whatnot. But I will like to come back to another remarkable aspect here later. One quantity of very high interest is the volume of water inside the air system. Here, the value predicted by SPH is very similar to the volume of fluid method, as you can see here, particularly for the finest spacing. Looking at the runtimes, we have a clear winner. So the finest resolution used in Prion Lab is 5 millimeter. This requires much more elements, so 6 times more elements, but it's still more than a factor of 2, actually a factor of 2.5 faster than the volume of fluid method, which uses an adaptive mesh. Please note that this was with version 3.3 without any refinement, and today the performance difference is much higher due to the adaptive resolution feature in Prion Lab. I will come back to this later. And there were also significant performance improvements that we made to our implicit formulation in the last years. So this was the comparison between Prion Lab and star CCM, so comparing two simulation methods. But what is much more interesting is comparing actually the simulation results predicted by one method to the real world test data. So therefore, the second objective was replicating the data measured in real world weighting, and therefore the vehicle speed, which is very decisive for the output of a simulation so if the car drives with different speeds, as we have seen before in these different regimes, this has a quite high impact on the overall fluid behavior. So, and normally these cars do not drive with a constant speed throughout this channel. This is not possible. So here Volvo collected the vehicle speed in order to make a similar setup than in Prion Lab. And the suspension data was then used, so it was measured and the free surface was examined in order to make a comparison. So free surface was visually compared, and the suspension data is a quantitative data that was then compared. Here, I would like to emphasize that there were modeling assumptions because it made, so in version 3.3, we had only a linear spring and damper model in Prion Lab. And in reality, they had a non-linear model, and only the wheel, brake disc, and calipers were considered unsprung parts in the unsprung parts in the simulation. So there were quite some assumptions, but the question is, can we still predict good enough the reality? And I would say yes, and Volvo is the same opinion. So here you see the front and rear spring damper system deflections on the two graphs on the right, and on the lower graph is actually the speed of the car, which you see is not constant, but some curve. There's a difference in the last seconds here for the front deflection, and this is due to the hydraulic forces, or due to the case that in Prion Lab, car suspension model is only exerted or activated by the hydraulic forces, but not on rigid contact. And here, and at this point in time, the car drives already out of the water. So, but interestingly, in this dashed part here, the values are in very good agreement. For the surface side, a visual comparison was performed. On the right-hand side, you see the simulation with Prion Lab, and on the left-hand side, you see the real-world data. And if you look closely, you see that they are in quite good agreement. Also, these three smaller bow waves that we have, and also the wave in water behavior in the back of the car are matching very well. Also, the surface level around the car. For the supercritical regime, we also see a good overall agreement of the deflection curve trends. But here, there's an underprediction, particularly for the front axle. And this is basically caused by the simplified linear model used in this older Prion Lab version 3.3. One thing I would like to emphasize here is that previously I have shown a force comparison of the hydraulic forces predicted by the volume of fluid method to our SPH method. If you remember it, there SPH seemed to overpredict the forces. But here, compared to the real-world data, it is rather the opposite, as the deflection should be, according to the test data, actually a bit higher if the forces were overpredicted. This allows for the question which simulation result should be trusted when comparing two methods with each other. And here, again, the visual results compared with each other. You see that there's much more action now in the water, which is matching quite well also from the surface levels around the car, the simulation. You can find all these videos also on our website if you want to watch them again and compare it for yourself. Yeah, so all these simulations that we've seen, again, this was performed in 2018, and we do still a lot of research and development. And in the last 2 years, we have developed a very robust and efficient strategy algorithm for refining and coarsening particles. So in these simulations that you have seen before, also there was always the front of the water was cut, so that the water was cut in front of the car. There, the workflow that we recommended to the user was to set those particles or deactivate those particles and activate them over time using the speed of the vehicle as an input for when to activate those particles. And this workflow worked well for most of the settings, but if the car speed was too high or the Froude number was too big, then the front wave might have traveled faster than it should be and reach those particles that have already that are still deactivated, and this caused, of course, problems. So now with the uniform resolution, with the adaptive resolution in Prion Lab, this workflow is not needed anymore, and you can simulate, as we have seen also for this Renault car, the whole domain very efficiently. Here we have 3 different levels of particle spacing with the fine spacing of 5 millimeters still around the car. And the simulation results are very comparable, and the total simulation time has reduced by a factor of 3. So instead of 3 days, you can simulate this whole setup in 1 day now. And what is also very interesting here is that the number of particles, of course, are minimized, and this makes also the post-processing more efficient. Yeah, it's also, of course, very important that the quality is not traded in for shorter computation times, and therefore we are making sure that our adaptive resolution solution is capable of predicting the results in a very good way and reliably. We have benchmarked this on several classical CFD benchmarks like the lid-driven cavity, or what is also very important for this kind of application is the Torricelli benchmark. Here, it's important because, as I mentioned earlier, we have these complex geometries. We need a fine resolution inside the engine compartment area in order to get the flow rates right. And if the particle resolution is too coarse, then the flow rate between these small channels would not match. And with this new surface proximity refinement, which just refines the particles around the hole here in this example, we get a speed up of 25 compared to the uniform resolution. So I'm slowly coming to the end of my talk. So in summary, I hope I could showcase that SPH can reproduce similar results as the volume of fluid method for the stationary setup at smaller computational cost. But what is more important, that in Prion Lab, a moving vehicle setup can easily be implemented because we do not have problems with moving complex geometry. We can simulate the free surface flow efficiently. There's no meshing required. So these all are the intrinsic advantages of SPH. And due to our reliable solver, we can replicate the phenomena seen in physical testing. And now with adaptive resolutions, we can have improved the workflow and also significantly shortened the turnaround time to simulate the whole domain without sacrificing any details. And so for you, the important takeaway should be that SPH has arrived in the industry now, and that the trend is increasing. So the number of SPH-based tools in the market is growing, the user base is growing, and so is the whole SPH community. So in my opinion, the future for particle-based codes is quite bright. And with this, I would like to close my talk and thank the SPHERIC committee once more for this opportunity. And I'm looking forward now to your questions.
All right, thank you, Marcus. It was a very, very nice presentation. So again, for everybody in the room, feel free to put your questions directly into the chat. That's probably the easiest way to do it. Otherwise, you can also raise your hand